Hi, welcome to my lab report for Physics 2212, Lab 6, Magnetic Braking. The purpose of this lab was to observe and analyze the behavior of a bar magnet falling through a conductive tube with both a real-life experiment and computational simulation, and the aim was to understand the electromagnetic effects generated during the magnet's fall, including the induced currents and opposing magnetic forces, by using core principles from electromagnetism and circuit theory. The main results from the lab include a real-world time average of 1.072 seconds for falling through the tube and a simulated model with 1.105 seconds. Some fundamental principles used include the Biot-Savart law, which is used to calculate the magnetic field produced by a moving charge, the magnetic flux, which is the amount of a magnetic field that passes through a surface area, and Faraday's law, which describes how a changing magnetic flux induces an electromotive force, or EMF, in the conductor. And also Ohm's law is used to relate voltage, current, and resistance, and the Lorentz force is used as it's the force on a current-carrying conductor in a magnetic field. These principles were applied to examine how the falling magnet induces currents in the conductive tube, which in turn produces opposing magnetic forces that slow the magnet's descent. For the real-world setup, the materials included a bar magnet, a 46-centimeter long tube wrapped in aluminum foil, and a video recorder, or phone. The tube dimensions include an inner radius of 1.5 centimeters and outer radius of 2 centimeters. And for each trial, the magnet was held above the tube, released, and its motion was recorded until it exited the tube. After 5 trials were conducted, the average fall time was calculated to be 1.072 seconds. The modeling approach was used in GlowScript, which is a Python simulation platform, and this simulation was created to replicate the experimental setup using the initial conditions based on measured properties, a function to calculate the magnetic field strength of a dipole, a function to create the magnetic flux through the ring, and also a loop to update forces on the magnet and its position over time based on the induced currents. This simulation generated a 3D visualization of the magnet falling through the tube, where the induced currents in the aluminum tube were shown as red being the clockwise current and blue being the counterclockwise current. And these current directions were determined by Faraday's law based on whether magnetic flux through the rings was increasing or decreasing. And from the simulation, it was simulated that the fall time was 1.105 seconds, which is slightly longer than the real-world time. And the simulation also visually represented how induced current direction changes depending on whether the magnet is approaching or moving away from a segment. The simulated time was 1.105 seconds, which is slightly longer than the real-world time of 1.072 seconds. This small difference may result from a slightly overestimated dipole moment in the simulation, or minor unmodeled effects in the physical setup, such as small air gaps, tape friction, or other slight angular misalignments. The velocity versus time graph from the simulation revealed a nonlinear cubic-like trend, where velocity decreased gradually at first, then more steeply, eventually reaching a nearly constant value of negative 0.417 meters per second, and the magnet maintained its terminal velocity at this value for approximately 1 second, indicating a balance between gravity and magnetic damping. And after that period, the velocity decreased further, suggesting a disruption of the equilibrium, likely as the magnet neared the tube's exit or experienced changes in the induced current field. To further this discussion, the question, what if the conductor's resistivity were near zero, was posed, as according to Ohm's law, it implies that with very low resistance, the induced current would greatly increase, and a higher current would result in a stronger magnetic field opposing the fall, potentially slowing the magnet even further. And the second question, what if holes or slots were cut into the tube? This would disrupt the ring currents, producing the magnetic damping force. And also, if the holes were asymmetric, it could introduce rotational torque, causing the magnet to spin as it fell. General conclusions from the lab include that the experiment demonstrated a falling magnet through a conductive tube induces ring currents that produce a magnetic force opposing gravity, therefore slowing the fall. The real-world and simulated times were very close in agreement, indicating that the computational model was highly accurate. Also, small differences likely resulted from real-world imperfections or slight variations of material properties. And finally, overall, this lab provided insight into how electromagnetic damping can be modeled and observed using core physics principles. Thank you.